Is it audible?
Yes, sir.
Sir.
Is the PPT visible? Is the screen visible?
Yes, sir.
Yeah. So in the last class, we discussed about one of the important modules of the LPC2148. So we have seen that we have studied about ADC converter in the last night. So how ADC converter can be used to connect to the 14 different sensors of the external world and convert them into digital value and provide in a variable the data for further processing. So today we will work on another important module, so which is also required when we are able to control the external world with analog data. For example, you want to produce the music, you want to produce sound, so you want to produce the voice. So what is the way? It is an opposite of ADC. That means that you have to produce analog information. So if you look at here, this module gateway converter, which just gives one line is there, one pin is there. So what is that one pin? This pin, if you just check in the oscilloscope, you can get different waveforms, different pulses like this on this waveform. If at all, if you look at the complete 64 pin of the LPC2148, there is no pin is available which can able to generate analog data except the single pin called A out. So that means that if you want to produce any external world analog in nature signal, which can be a voice, which can be some other variation which can control the motor, anything which is analog in nature, which changes with reference to time, there's only one pin is available among the 64 pins, that is analog output pin. So this analog output pin will be generated by a module called as DTI converter, which is present inside. If you observe the Arduino boards when you work with the projects, Arduino do not have a DTI converter. We just simulated the analog signal using a PWM concept. So having a DTI converter means that is in a hardware module. Inside the hardware, we have implemented the DTI concept. So simulating analog signal using a PWM is an approximate method. The better and the most precise and which is a more finer quality of analog signal you can generate when you have a DTI converter hardware is present inside the microcontroller. So LPC2148 provides such one DTI converter. Sometimes what will happen whenever the microcontroller do not have a DTI converter, we purchase this chip from externally and then we connect that chip to the microcontroller and generate analog signals. So LPC2148 has the DTI converter inside that one. Now, what are the things DTI converter can do it? So as the name says, DTI converter can take what? Can take the digital data as an input. So who writes the digital data? The programmer writes into that, and the corresponding analog output I can able to produce it. So we will see that how exactly I can able to use the DTI converter module. So some basics of the DTI converter. Any DTI converter, if you just look at the DTI converter, what does it has got? It has got some digital input. So if it's an 8-bit DTI converter like a DAC 0800, which is very popularly used in earlier microcontrollers, it is from a National Semiconductors. It was an 8-bit DAC. Even today, so many projects uses this chip. So this chip take the digital input and produces analog output. So it has got a settling time of 100 nanoseconds. Like I said, in case of an ADC, always the moment you give the input, it takes some time to convert the analog data into digital. That is called conversion time. So every ADC takes certain time. conversion time. Similarly, DAC will also take certain time to convert digital and put the proper value on that one. That is called as a settling time. We call it a 100 nanosecond is a settling time. So it is better to have a less time for settling, so that you can able to produce a higher frequencies or higher bandwidth waveforms. You can able to produce it. So the settling time is 100 nanosecond here. Now let's see that if, for example, if the DAC is an 8-bit DAC, so what are the terms and technologies we have to understand with reference to the DAC? So what is the combination of inputs I can give if it's an 8-bit DAC? So the minimum is 00, the maximum is I can give 111. So corresponding to each digital input, you have one analog voltage will be produced. If the DAC is being configured to work from 0 to 5 volts, so 0 corresponds to 0 and the last one corresponds to 5 volts. Let's now understand what is the resolution or the step size of a DA converter. So it is just exactly opposite of what we studied in case of a ADC. So here, now instead of giving analog input, I'm giving a digital input. Now every 1 bit, if I change it, let's say I have produced 000, next I'm going to produce 001. The 1 bit change I'll make at the input. Now for every 1 bit of change at the input, what is the corresponding voltage change at the output? That will be called as a step size, or it's called as a resolution of this your DAC. That means that any voltage less than that, you cannot produce it. You can produce only that voltage. Now, again, the maximum voltage, whatever you design, that depends upon the reference voltage you connect to the DAC IC. So in this case, if I take a reference voltage as a V reference as a 5 volts, then what is the resolution of this DAC, 8-bit DAC? It is, we know that 5 volts divided by 256. That means that resolution is what? 1 part in 256. Every bit change produces how much of analog voltage. So what is the resolution of this one? 5 volts divided by 256. So 20 millivolts is the resolution of this DAC. So you cannot produce a voltage less than this one. If at all, if you want to produce a less than this voltage, what you do? Change the reference voltage so that you can able to achieve even a smaller voltage, you can able to produce it. Now, so it is always better if you go for more number of bits. If the number of bits increases, then what will happen? So your denominator will increases. Whenever the denominator increases, what will happen? Again, the resolution improves. That means that you can able to produce even a small changes. Either increase the number of bits or reduce the reference voltage. These are only two ways possible to have a better resolution in case of a DAC. Now, so if you do not have the DAC, you have to provide outside the microcontroller. But fortunately, we have in LPC2148, we have a DAC module present inside the chip. So we will study now what is the behavior, what is the parameters, what is the system configuration of the DAC module present inside the LPC2148. Now, so I've just taken the LPC2148 chip. I'm just here indicating the DAC module here. Now, whenever you have a DAC module, let's see that what are the pins is required in a microcontroller. Now, ADC and the DAC, these are the only two modules which are analog in nature inside the LPC2148. All other modules are what? You are I2C, everything is about digital in nature. So whenever you require ADC or DAC module, I said you have to use two different voltages for the chip. One is what? VDD analog and then VSS analog. So these are the two separate pins compared to the VDD and VSS provided for other logics. But it is better to provide a separate voltage from the different sources to these one to reduce the noise and have the better performance of your ADC and the DAC module. So if not provided, you can always use the same VDD for the VDDA, same VSS for the VSS also. And as I said, V reference decides what is the resolution. So V reference is also a separate pin. Generally what we do, V reference also we will connect to the VDDA so that whatever the VDDA will be same as a V reference. Now, and these are the power supply related to the ADC and the DAC module. So what is the output pin provided for the DAC module? Only one pin, that is called A out pin. So what is it? As I said, every pin is being multiplexed with the multiple functions. Now A out is multiplexed with a P0.25. So the P0.25 can be behaved as what? A out. So you have to suitably use a pin selection register and configure the P0.25 to act as what? A out pin. Now, so once I know the hardware configuration for the DAC module, then as a programmer point of view, what is visible to a programmer? So as a programmer, so what you can do is you can write some data into the DAC module. So whenever I want to write some information into the DAC module, what is visible to me? there is only one register is present inside that register, which is visible to the programmer and which is used most of the time by the programmer. What is that register? Called DAC register, DAC, or means DAC register. So what is the size of a DAC register? We know that every register is of 32 bits. So DAC register is of 32 bits. So this register is available to the programmer. What is the purpose of this register? You have to write the digital value. That means that we know that this DAC module is what? 10-bit DAC. 10-bit DAC means I can have the input from varying from all zeros to what? All FFF. That means that in hexadecimal 00 to 3FF. This is a range of digital data I can write into this register. But as I said, the register is a 32-bit, but I am interested to write only what? 10-bit into this register because your DAC is a 10-bit. So what they have done in this register, 32-bit register, they have allocated certain bits. If you write the value into that bits, so then it will corresponding to what? DACR, that corresponding to the value of the DAC. So we will see that now. What are the values for that now? So this is the register. So this is the register. In this register, 32 bits are available. These are bit allocations are there. So bit 0 to 5, it's reserved. Only bit 16, bit 6 to 15, the bits are used in the sense. So this register is what? Is a 32-bit register. In that, how many bits I'm using? Only the following bits I'm using. Only these bits I'm using it. So what is that bit? These bits corresponding to what? The bit 6 to bit 15, because this corresponds to 10 bits. So you have to write the digital value, that is a 10-bit value, which is present in any of the variables, into exactly in these bit positions. You should be able to write it. Then only what will happen? This will be picked up by the DAC and converts into corresponding analog voltage and puts it on a pin called A out. So this is the only thing in the program you have to do it. How we can do it? Let's say you have the data in a variable. You have a data in some variable is available. So some data. So what is the value you can have in the variable? I can have from 0 to 1023. So this value, if you want to put into this one, what you do it? Take this variable, left shift by 6. So take the variable, left shift by 6, and then write into this DSE register. Then you write into the DAC value. So this how you can get the information into this one. So this is about the hardware and the programming aspect of the DAC register. We'll start writing the program and start learning how a DAC can be used to generate different kinds of waveforms. So before we move to that one, let's understand what is the resolution of that. So you know that the resolution of that is what? Since this chip is a 10-bit ADC, the resolution is so 3.3 divided by 1024. Here I'm assuming the reference voltage is 3.3. Since it's a 10-bit to the power of 10, the resolution is 3.2 millivolts. So what is generally asked in the exam? So in the exam generally asked, if I give digital, let's say 100, if I give it a digital input, what is an analog output produced by the ADC? Then how do you calculate it? So we have done the reverse of this in case of an ADC. Now how do you calculate an ADC here? So that means that every 1 bit of digital input corresponds to what? 3.2 millivolts. That is 3.3 into 1024. If I give 100 as a digital input, what is the analog voltage corresponding to that? It is nothing but you have to say 100. So into the resolution, whatever the resolution. Now, so what is the resolution? Let's say resolution is nothing but in this case, let's say 3.2 millivolts. So 100 into 3.2 millivolts is the actual analog voltage produced at the A out chip. So this is, you can observe in the multimeter. So this is what you can get in the A out chip. So if I give, for example, 1023, so that means that, so 1023 into resolution, that means approximately 3.3 voltage you are going to get here. So this is how you can convert given digital value into analog voltage. Let's take another example. For example, if I give 200, so what is the analog equivalent of 200 produced at the A out pin? 200 into 3.2 millivolts. That is an analog output you're producing at this point here. So this is the one general quiz question we generally ask. We ask you what is the digital input given. So you have to compute analog output. I am assuming here the reference voltage is what? 3.3 volts. If my reference voltage is 2 volt, my calculation will be different because the resolution will be, instead of 3.2 volts, resolution you have to calculate as what? 2 volts divided by 1024. So this completes about the discussion about the hardware, the programming, and the resolution of the DAC module. Now we will go to directly to the program. So hope you are able to see the screen. Is the screen visible?
Yes, sir.
Yeah.
Yes,
So
sir.
now I will take the simple first basic program. So then we'll go to the different programs. Okay. So now we will use a DAC program now to generate different analog voltages using the program. Now we will see that how we can able to do that one. I'll go step by step. So since I'm not using any LED here, so these logics are not required. Okay, I'll remove that. Okay. Now, so what is the first thing I had to require it? What is the first thing I require? Now, so whenever we start the program, always remember that the pin whatever you used is, look at the pin here, A out. It is being shared between what? P0.25, AD0 and the A out. The same pin which is meant for A out is also meant for what? P0.25 and AD0, AD0.4. Then what should I do it? I should be able to configure this pin as A out, not as a P0.25. How do we configure? That is the first step I have written here. So what is the first thing I have to do it? Identify which is the pin selection register it is being, you have to use it. We know that pin selection 1 is meant for what? P0.16 to P0.31. Since this corresponds to P0.25, I am taking which is a pin selection register? Pin selection register 1 I am taking into the program. Now, now identify in the pin selection 1 register which are the bits corresponding to the pin P0.25. How do you do that first? So we know that P0.25, so from that pin I can know that number is what? 25. Subtract 25 minus 16 because it's starting from the 16, so you get 9. So now 2 bits are required for every pin, for each pin. So then what we'll do? Multiply 9 into 2. That is how much you get? 18. So the bits 18 and 19 in the pin selection 1 register corresponding to what? The P0.25. Now I have to configure in what option? So if you look at here, the configuration I supposed to do it what? So first 00 means what? P0.25. 01 means what? AD0.4. A out means what? That is 10. That is, so this is a second alternate. 0th alternate, first alternate, second alternate. So I supposed to write in the bits 18 and 19 what value? That is 10 I supposed to write it. So now 10 is nothing but what? 2. So 2 is nothing but 10. So what I'm doing first, I am just clearing the bits 18 and 19, writing first 110 into that one. That is, we have studied this in the probably in the session video session LPC2148 and the second lectures. This is how we can clear the bits first. So first I have to clear 18 and 19 bits to 0. After clearing that, I am making those 2 bits as what? The combination called 1 and 0 I am making it. So how do you make 1 and 0? Write 2 at the bit numbers 18 and 19. Use the OR operation. So using this combination, I am setting the proper value in the pin selection 1 register to configure the P0.25 to work as A out, the second alternate function. If you don't want all this one, you want to simplify another simplified method, you can write like this also. Pin selection 1 is equal to 0x00800. This 8 corresponds to what? Bit number 18 and 19 corresponds to 10. You can write like this also. Only thing is when you write like this, so you are disturbing other options of the pin selection 1. Since this is the only experiment you're doing, you can write like this also. But when you're developing the products, you can always like this so that you're not modifying the other bits. So now for experiment, you can write like this also, you can write it. That's what is given in the manual. Now, so after that, I just set some LED and 25, that is analog A out as a output pins, IO direction, I just set it. So then I'll start my logic here. What is the logic? I said, you can access the DAC module using a register name called as DACR, is a 32-bit register. Now, whatever the value, I declared one variable called value. This is an unsigned integer. Now, this value, now I'm using to represent the digital value. What is the digital value I can represent here? The minimum is 0. Maximum is what? 1023. These are the values I can write. You can write more into the variable also. Variable can take it, but it does not permit you to write into the DACR register 10 bits because 10 bits maximum is what? 1023. Even the variable value can be more, but you cannot fit in the 10 bits. So that is why you should limit from 0 to 1023. You know the value. It's a digital value. So write into the DAC module. How do you write into the DAC module? So push that left by 6 and then right into this one. So this I've told you in the beginning. That means that DACR is a 32-bit register. The bit 6 to bit 15 are meant for the 10 bits of the DAC module. That is why I'm just shifting left by 6 and then writing the whole value, that is 10 bit, into this register. Now, the moment you write this one, what will happen? You go and measure the A out waveform in an oscilloscope, you get the corresponding value. Since I write 0, what do I get? 0 only, I'll get it. Now I give some delay of 10 milliseconds. Then again I have written what? 3FF. 3FF is what? The 1023 maximum value I have written here. Then again I have written into the DAC. What is the value you'll get? That is 3.3 voltage. So you check in the oscilloscope, you get a 3.3 voltage. Like this, I can able to output to the DAC module any digital value and produce a corresponding analog voltage. So in this program, what I have done is I'm just first sending 0. I'm just sending then maximum 3.3 volts. I'm just alternating one after the other one so that you can get a square waveform. So we will analyze this program now, how it works. So I've just compiled the program. So now I'll go to the debugger. Now, so I have set certain things. What are the things I've set? In oscilloscope, I created what is called A out. Type in capitals A out and enter. So you can able to note, you can able to monitor A out signal on the oscilloscope. Configure the display type as analog and then close it. So I've done the required input configuration here. A out, analog in nature, and then close it. Then so I have used, so this is not required. I've used a pin connect block. So to demonstrate, that is P0.25 has to be changed to what? It should be changed. Now it's a GPO by default. It should be changed to what? A out. And this I just dragged that DTA converter from the peripherals. I dragged it. What does a DTA converter contains? I said it contains only one important register that is called as DACR register. See that 32-bit register. In that 32-bit register, the 10 bits is nothing but value that has been represented separately. So bias is there to select the different settling time. So I am not interested in the settling time. I've taken a default settling time. I have taken it. In the project, you can always choose whether you require different settling times. So you can choose, you can make this bit is equal to 1 or 0. Then what is the voltage reference I applied? 3.3 volts. Good. So I have just changed reference voltage. I've selected to 3.3 volts. If you change this one, A out values also will change accordingly. Now this is the DTA converter. I have it. Now we'll execute the step by step. First, I'll configure this pin to be act as what? A out. So I'll do the step by step. So see that I finished. Now look at that. The P0.25 has become what? A out now. It becomes analog output pin of a DTA converter. So what is the option? It has gone to the second alternative, 0th first, and the second alternative it has gone for it. So for a moment, one moment. Okay, so now I will execute the next instructions. So now I'll come here. The moment I write something here, it will come to DAC register. You can just observe that. So value 6, the value is written 00. It was earlier 00, same thing is there. Now I'll execute the delay program. Now I write 3FF. The moment I write 3FF into DAC, see that it has become 3FF here, and your output is what? 3.2968. That is approximately 3.3 volts. You'll get it. Now, so this value, whatever you written here, should be able to monitor the oscilloscope also. So I just given, see that now what will happen? It was 0. Now immediately your A out becomes what? It has become a high because 3.28. Now I'll run this program. See that it was 0. Now it has become what? High, 3.3 voltage, because you change the value here. Now I run the program so that it repeatedly runs this program, that is 0 and the 1. So let's say I'll run the program. You can see that now you can see that. So the program is changing here. Look at here. It is 003FF. I'm writing a different values. You're getting the square waveform on the oscilloscope. You're getting a perfect square waveform on the oscilloscope. So this is how we can able to implement different types of waveform or different types of analog patterns you can generate on the A out. Now we'll go to other programs. So I'll stop this program. I'm audible.
Yes, sir.
Yeah.
Yes, sir.
So now I have got one waveform I got generated. So summarizing this program. So what are the 3 steps required? So configure the pin P0.25 as an out. Then write the proper value into the DACR register. So that is only the 2 steps required to use the DAC module. So now I will show you how to generate a triangular waveform and a sawtooth waveform. So now, since I require more number of waveforms are required, I'm using certain switches to select which waveform I require. Look at this program, what I've done. I've defined certain switches. So switches is nothing but what? Input pins. So I have connected to P0.14, P0.15, these 2 pins, 2 and 3. The switch 4 and 5, 6, I have connected to P1.18, 19, 20. You may ask, sir, why you have taken like this? So these are the pins we have used in the kits, used in the college. In our college laboratory, the switches whatever we provided are connected to these port pins. That is why I taken the same things. So P0.14, 15 and the P1.18, 19, 20 are connected to switches. How many switches? 5 switches are required. Now what is my job? I have to generate a different waveforms based on the switch. If I press switch 14, I should generate a sawtooth waveform. What is a sawtooth waveform? So these are all common. These are all whatever we discussed earlier. Now we'll go to the program. If I press switch 2 equal to 0, or that means the switch 2 is pressed, then what does it mean that? So whenever we press the switch, it becomes what? Low. If you don't press the switch, it becomes a 1. That is what we studied in the previous sessions. So if whenever the switch is pressed, it becomes 0. I'm checking for that. If it becomes 0, I'll enter to this logic. This logic is a generation of a sawtooth waveform. What is a sawtooth? We know that sawtooth waveform is nothing but going from 0 to the maximum voltage and again coming back sharply to the 0 voltage and again continue. This is called as sawtooth waveform. So I'm just starting the value from a 0. I keep incrementing the value until it reaches 1023. Whenever it reaches 1023, I'll again make the value is equal to 0. So each one while loop produces one sawtooth waveform. It reaches from 0 to 1023 and it stops. Since after that, say after the if switch, after that when this while loop is over, then it falls apart from this if statement. It will come out of this if statement. So it comes to what is called as, so if switch 2 is there, it will be here. So it comes back here and nothing else is satisfied, else is not satisfied, this else is also not satisfied. Then what will happen, since it's a while loop, it's a continuous while loop, so it's in this while loop, it's a continuous while loop, so it again come back to the same logic. It will again do one more sawtooth waveform. So like this, I have just provided this in a while loop. That means that if switch is continuously pressed, so every time it comes to only this logic and execute one sawtooth waveform. So if you run continuously and the switch is pressed, you feel that, oh, sawtooth waveform is continuously generated. So even though it's a one shot, it's generated. So it falls apart. Again, this logic is satisfied. It keeps executing only this logic. Since I have not pressed other switches, else this logic will not work. So this logic will not work. So only logic which works what? Only logic this is works continuously since in a while loop. So this is a concept I've used to generate different types of waveforms here. Now, now I'll run this program to see that how does it work. So now I'll compile this program. So to make the switch operation, so what I'll do is I'll just pull the peripheral port 0.0. So I have connected to P0.14. You can just look at here, P0.14. So that this is a 14-bit I'm using for a sawtooth. The switch 3 I've used for a triangular. I'll show you triangular, the logic later. So let's go with the 1. I'll run the program. Now it's high. You can see that the waveform is high. Now if I press the 14, so this is a 14 pin, I'll press it. You get what is called sawtooth waveform. Just I'll zoom out a little, zoom in. So you can see that. So this is a perfect sawtooth waveform. So if I just stop for a moment, so see that it has increased step in terms of steps. First 0, then 1, 2, 3, 4 like that. And I'm outputted to what? 1023. It has reached the maximum 3.3 voltage. And again, you start with a 0. So then it continued. So this is how you can see the values are changing here. So how the values throwing at the DAC register, so is producing the corresponding voltages in the out. See that the voltage produced here. So it's been keep changing through the program control. So this is how the program for Sawtooth waveform. Let's now analyze the triangular waveform. Now, so you know, you would have got by this time idea what is a triangular waveform. It's nothing but a positive sawtooth and the negative direction sawtooth. So first I'll produce a positive sawtooth from 0 to 1023. Again, I'll make another while loop. So here I'll start decrementing the 1023 to 0 value. So I've just decremented this value. So that means 2 while loops I given, one while loop 0 to 1023, other one 1023 to 0, and run then when the switch 3 is pressed. So what is the switch 3? Switch 3 is in the pin number 15. So it's already there. I'll just compile the program. Now, so you can see that as soon as I run the program, it has become high. The waveform become high. Now 14 and the 15. I'll go to press the switch 15. So you can see that. So you can see that. So I'll stop. See that triangular waveform is coming. So the values are increasing to 3.2, 3.3, and then decrease to 0. So this is how you can see that. So triangular waveform can be generated at the A out signal. So now we've understood that using this concept, step waveform can be generated in steps. Steps of 5, steps of 15, steps of 20, like variety of waveforms you can able to generate. But make sure that the minimum value is 0 and the maximum value is 3.3 volts. Using that, you can able to generate. Now we will go to a very important concept in the waveform generation, the concept called as lookup tables. Whenever you want to generate the waveforms, always the two types of possibilities are there. One is using the program to compute analog voltage at the runtime. That is what we did now. That means that at the runtime, you are varying the values of the value. At the runtime, you are varying the value of the value. At the runtime, you are varying the value of the value variable. Because why? You are doing what value plus plus or value is equal to some value, you're doing it. At the runtime, at the program, you're generating it. So this is very possible, recommended for a waveforms like triangular, the sawtooth, rectangular waveform. Look at what will happen if I want to generate a waveform like a sine waveform. Let's say I want to generate a sine waveform using a DAC module. So then how do you get the different values which is to be outputted to the DAC register? Now every time you want to get the new value to a value variable, you have to use inbuilt function called sine function, cosine functions like that, you have to use it. We know that whenever you call the sine function, it takes some time to calculate and get you the value of the sine function. That is theta, you have to vary from 0 to 90 degree or 180 degree. So you should think that these functions are implemented on the microcontroller, which is completely integer based. Do you know that have you studied in assembly language programming any instruction which handle floating point numbers? No. So the microcontrollers, the instruction set is completely integer based. Yes or no? You have only the 32-bit number, integer number. But whenever you are implementing algorithms like sine, the floating point comes into picture. Then how do you implement? That means that software algorithms have been developed to handle the floating operations using integer arithmetic. So algorithms has to run. And you should think that microcontroller is a small chip. The computation capability is very less. So at the runtime, if you want to do computation and get the value and then output, it takes its own time. That means that waveforms will not be accurate and waveform will not be reliable. So you should always remember that. What is the reason? Since embedded systems are not compute capable and requirement of real-time data, the pre-computed values for different sine angles and stored in a program or code memory are used to generate waveforms. So what does this mean? That means that instead of calling the sine function at the runtime and calculating the value, you calculate beforehand itself, before you run the program itself, what is the value of sine 0, sine 1, sine 2, sine 3, different degrees. Keep these values in one array. So in a single dimensional array, we call it a table, lookup table, you keep that. Then at the runtime, whenever you want to generate a waveform, take the values from the table one by one, just output the DAC register. Then what will happen? The time taken for every output of every value of a sine waveform will be similar. No time gap will be there. So it will be linearly. That is when you plot the time versus your output voltage, every point, the time will be perfect. It will be same thing. Because why? You're not using an algorithm. You're not using a program to compute. You're just picking from the table. It is the same for all the values. So that means that, so your waveform is more accurate and it's also fast. You can able to produce higher frequency waveform. So that is why the second method is also extensively used in embedded systems to generate different kinds of waveform. For example, if I want to produce a recorded message, what do you mean by recorded message? For example, you have seen that in a if you go to the airports and everything, a lot of recorded messages you listen. So how do they produce embedded system? So they stored all these recorded messages into the values and put in a table. So we will get one by one value and throw to the DAC module, and they put on just an amplifier, simple amplifier. So whatever you use for the mobile amplifiers, that you can connect to your microcontroller module also. Then you will get a recorded audio. So that is the same technique they follow. It's called as a lookup table method. So the waveforms are simple, go for this method. If the waveform is complex, go for this method. Now let's write a program and understand how we can implement lookup tables method of generating the waveforms. Let's look at this program now. Now one small example is given here. So in the lookup table, whatever the waveform you require related to that waveform, one cycle. So for example, if it's a sine, I have to prepare what? Data for one cycle. If I'm doing what is called as full rectified, what is one cycle? This is one cycle. For a full waveform, full sine waveform, this is one cycle. Prepare the number of samples of the values required for one cycle and store it in a table. So I've just stored in a table. If it's an audio recorded message, store all the samples of your audio in this table. Then find out how many number of samples are there in array. Just define that in a variable. So now, while count minus 1, I'll just take from the table one by one, starting from 0 to all the values, and then output this value into the DAC register. So then you get a waveform. See the simplicity of this method compared to the previous method. Even this waveforms also, the sawtooth, the triangular, you can able to generate using this method. Only thing what you have to do is you have to store the values, all the values, how many values you require. Let's say if you want very accurate waveform, you can say that 1023 here and another 1023, 2000, the 48 values you can store it. If you don't want that much of accuracy, you can store in between some values, and you can store in this table. It depends upon how much you accurate. It's not required you have to store all the values required. Say you can give in between values, and you can also store. If you want more accuracy, prepare everything, put in a table, because anyway code memory is huge. For example, in LPC2148, you have a code memory of 512 kilobytes is there. Whatever the project you take, it will not go more than 100 kilobytes. So unless you use an RTOS into the coding. If you don't use an RTOS, your code will be less than 100K, so that you have a lot of space available in the code memory where you can store all these tables. So these tables will be part of a code memory. It's not part of a RAM because it's a fixed set. So whenever you make the tables goes to the code memory, not RAM, include a keyword here called code. So include a keyword called code in the declaration of your program. The moment you say, short integer code table, or so if you say that, then that means that assembler or a compiler understand that you are instructing the compiler to store this data into a code memory. There is a flash memory. It will not go into the RAM. If you don't give this abbreviation, it will store that in a RAM. So always using this technique, you can always put them into a code memory. So that's why it's always better to have use this technique to get a reliable outputs and more accurate outputs. Now let's implement the Sine program. Sine program for this. Now let's look at for a sine, what is the formula for this? Now this is the waveform I supposed to generate using the DAC module. Now we know that the whole of the sine should be fit in what? Between the only two ranges. What are the two ranges? Between the 0 voltage and 3.3 voltage. So I will allocate the sine waveform in this shape. So 0 means what? Negative half cycle bottom. The 3.3 mod, the positive half cycle upper point. So I will arrange like this. Now, so the points required here to produce from 0 to this point, you can see that. So I start from 100 because you can look at that. This is 0. So this is a 0, and the in between point is what? 100 is the in between point. That is 100 is the in between point. So from this point onwards, so I have to produce this output. So I'm starting from 100 because why? From 0 to 0x1ff, that is half the value that has been here. Then from here to here is what? So 200 to 3ff. So I've divided all the values from 00 to 3ff into two portions. So 002 1FF is the first half of it, and then 2002 3FF is the other half of it. Now, so to find out the different values to be put in the table, so I should be able to vary the theta value. So what is the formula I've used? So this is the formula: 512 plus 511 into sine theta. This is the formula I've used it. Now I'll go to the here. So you can look at, this is the formula I've used it. So 512 plus 511 sine theta. Now, so 512 corresponds to what? 1 FFH. That is the middle value. So what I've said. So 512 correspond to what? The middle value. So that is 1 FFH. This corresponds to that middle value. So I've taken this one, 512. So the middle value is what? 512. So this value is fixed. Then using this middle value, I'm able to produce upper portion. So where do I start? From the middle value I start. What is the middle value? From the, this is the 0 to middle value is what? 512. So I've taken the 512. From there, I want to take the different samples to produce this waveform. How do you get the different samples? That is a formula is what? Sine of that. It's a sine shape. That is why sine theta I taken. What is the maximum you'll get it? So this maximum is value is what? That is another 512. That's why I taken 511. So it's a no. What is the sine 90? Say let's say if you go to the sine 90, it's a 1. So that means 511 into 1, 511, 512 plus 511. That is 1023. You get it. So that means that the top value should represent 1023, and the middle value will be what? 512. In between, I should get the different sine values. I should be able to get it. So that I'm varying between the theta. So this is a formula. I've just taken it to get the different samples or different entries into the lookup table. So now I change the theta. It is not required, as I said, to calculate all the values of theta. Theta 1, theta 2, give in 6 to 12 degrees I have taken it. So it will be approximate. You can make it more accurate. So I varied 0 to 6, 12, 13 like that. I found out the different values. Now, how many values are there? If you count it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 is there. So if you start from the 0 index, that is a 15. So otherwise 16 different values are required to be stored in the lookup table to produce what? This waveform. This waveform. It is like a 16 different samples. You know, you got it. Similarly, how do you produce this, the lower waveform? Nothing but the same values already, whatever you calculated, throw them in the opposite direction. You know that you have to throw them first from 0 to 511. Then again, throw the same outputs from 510 like this in the reverse order. You have to throw that so that you get what? This values also you get it. Now this waveform is ready. Now first off cycle is ready. Now the second off cycle you have to produce. How do you produce the second off cycle? So instead of 512 plus, what I'm doing is instead of plus, I am using a minus here. So all the values will come down now. So same values, whatever I already calculated, I said now minus value. Already the values are there. So I'm just doing the 512 minus these values. I'm doing. So you can just look at these values. Output the above values in the reverse order to get the other portion of the top half cycle. Add 512 for the top half cycle and subtract from 512 for the lower half cycle. So this will be the 0 when you subtract. So this becomes the lowest value possible, whatever. And it starts like that to get this 1. So now I'm for this one. Now this sine table values have been stored in this table. Look at this all the values. So what are the values I have stored? So from 512 plus 0 degree, 512 plus 6, that is a sine 6, sine like that. I have stored all the values. Cycle, that means that it produces like this. So now again another set of values I had stored in the reverse order. I started from 511, so I subtracting 511. So I'm just start reducing the order. So I got another half value. So the same thing, 512 plus I'm using the minus values I started here. So so what are the values I given here? I just started that one. 512 minus 106, 58 minus 208, like that I start reducing this one. So this is another of waveform. So these are the values I've just calculated to get these values. So now I will take these values, I will just put these values in the program. So when I take these values and put these values in the program, I you can get exactly the sine wave. You're able to get that values here now. So look at the program here. So this is the program I have taken here. So what is that? Since there are, I know that, so there are 15. So 15 sets are there. So totally, if you calculate all those things, it will come to be 60 entries are there in a table. I've taken all the 60 entries. So I'm putting in a table. So what is the name of the table? Sine table. Now I have just if this is not 60, I'm outputting the 1 by 1, and then I'm just producing this one. This is not, this is for setting the bias. You can just output the value. So when you run this program continuously, you get an exactly same waveform. And for the rectified waveform, because in the rectified waveform, you have only values like this. That is not the 60 values, you have only 30 values of that. You can just check this one. So this is for the triangular waveform, we have already seen. This is like a Sawtooth waveform. So I wanted you to go through this program, what is there in the already notes. Please output this value in the key forms. So since I'm just engaged here, so today lab, you are required to demonstrate both the ADC program, both the waveform generation of this program in the DAC program. Please keep it, type the program ready so that you can able to start demonstrating the program. So if any doubt is there, you can raise the doubts. So
Sir, can you please repeat which program do we need to show today?
afternoon, you can